All right, any other questions, issues, concerns, problems, anything whatsoever? And my phone's ringing downstairs and it can ring. Okay. So, any questions? If there's none, then I guess we're going to get started today. And where we left off last time, by the way, we're in Chapter 4, Trigonometry. 4.6, Graphs of other trigonometric functions, meaning tangent, cotangent, secant, and cosecant. We've done the tangent and cotangent, and now we're doing what they call the reciprocal functions, the secant and cosecant. And we've already shown how to do this, and why did this change? Okay. I had it on the right slide and now it's not. Okay, here we go. We're at the bottom of page 311, the paragraph at the very bottom of the page there. In comparing the graphs of the cosecant and secant functions with those of sine and cosine functions respectively, notice that the hills and valleys are interchanged. If here is your sine function here, you have it starts at 0 here. That's a dead giveaway. That's a vertical asymptote for the cosecant, because the cosecant is 1 over sine. You can never divide by 0. So the y-axis here is a vertical asymptote. They don't color it in, but it is. But then the max here for sine becomes the min for cosecant. Relative maximum here for sine, relative minimum for cosecant. When it goes back to 0 here, another vertical asymptote. When it, oh, here comes Jared. So let me get Jared here. Well, I already marked Jared here by mistake, I think. No, I didn't. Okay. I think I marked him rather than Matthew. Sorry, Matthew. You've been here. Okay. Well, I've got you marked now. I'm all the way across the page, so it's hard to keep the line straight. So I should have 3, 4, 5, 6, 7, 8, 9, 10. Should have broken double digits with that one. Did we? Looks like we did. Nobody else waiting. Okay. All right. So like I was showing, then when you run into another 0 here, of course that makes a vertical asymptote for the cosecant. A 0 on sine, vertical asymptote for cosecant. Okay. Then when you hit the minimum for sine down here at 3/2 pi or wherever it happens to be, then that's going to be the maximum for your cosecant. Okay. And then when you hit the 0 for sine again at 2 pi, another vertical asymptote there. So basically what I say is on the max and the min, they kiss and go in opposite directions. The cosecants go up here and sine goes down. Here the sine goes up and the cosecants go down. So that's what's happening. So it's really, you need to use your 5 points to graph your sine or your cosine curve, but then once you got those done, everywhere the sine or the cosine is 0, put a vertical asymptote, and oh, here comes Morgan. Let me get Morgan here. Okay. All right, Morgan's here. That gets us up to 4, 8, 9, 10, 11. I think that's right. Let me make sure. Whoa, no, here's Izora. Let me get Izora. At least her phone's here. Okay. There we have it. Okay. All right. All right. I think we got all here who are here, those who have just come in. So we should have 12 students. Oh, we just lost somebody. But hopefully they'll be back. Okay. Let me make sure nobody's waiting to come back. No. Okay. Hopefully they'll show up in a minute. All right. So that's what we've got. And so really, graphing secant and cosecant, all you do is graph your cosine or your sine, and then everywhere you see a 0, put a vertical asymptote, max or min, put that point in common, and then make sure the secant and cosecant go in the opposite directions from your sine and cosine. That's it. That's how you graph them. Your key points you plot for sine. Oh, here comes Kelly coming back in. She must have been the one that had to drop out. Okay, let me make sure she's all who are in the waiting room, and she is back in, I hope. Okay, so that's how you graph them. Let's see if we can move the slide on. Additionally, x-intercepts, I've already said this, of the sine and cosine functions become vertical asymptotes of the cosecant and secant functions respectively. That's what we do. The max and min become min and max. The zeros become vertical asymptotes. So let's do this one. What have I done with my pen? There it is. Okay. Now, sketch the graph of y is equal to 2 cosecant of x plus pi fourth. Okay? I don't want to do that. I want to graph instead y is equal to 2 times the sine of x plus pi fourths. I like sines better than cosecants. Why do I do this? Because they're reciprocal functions of each other. So let's start with our sine here. Start with the alphabet. A is equal to 2. That relates to the amplitude, which is the absolute value of A, which is also equal to 2. Then the B here is 1. That relates to the period, and the period is, for sine, is 2 pi over 1. Well, that's just 2 pi, okay? Then determine the intervals. Take the period, 2 pi, and divide by 4, and that makes the interval pi halves, okay? 2 pi divided by 4 is 2, and the 4 will be 2, so it's pi halves. And now we have a phase shift. The C, now remember this is always a minus, the opposite of this, so this is minus, minus, minus pi fourths. That's your C. That's the phase shift. That means it's to the left, pi fourths. Okay, now even though the interval is pi halves, we need to draw our graph in, I've got to move y'all over. Kelly, you're in the way. I'm going to scoot you to the right some. Okay, there we go. We're going to need to do quarter pies, not half pies, because you have to account for your phase shift as well. So here's going to be my vertical axis, supposedly. Here's going to be my somewhat horizontal axis, supposedly. And we'll just tick off a few points. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. On this side, negative 1, 2, 3, 5, 6, 7, 8, 9, and 10's out there somewhere. Up here we'll go 1, 2, 3, 4, 5, 6. We could go higher if we wanted to. Negative 1, 2, 3, 4, 5, 6, and maybe even a 7 down here and a 7 up here. Why not? Okay. Now, horizontal scale, these are your pi fourths, the fourth pies, not the half pies. Normally that would be our interval, but it is our interval, but we're going to do it in quarter pies. So this will be pi fourths. This will be pi halves. And that was 2 of those. So 4 of them will make a pi. I love that sound. 4 more, 1, 2, 3, 4 would be 2 pi here. And going to the left would be a minus pi fourths. That's the important one. Minus pi halves here. Minus pi over here. And 1, 2, 3, 4, minus 2 pi here. Now going up, I think I'll stick with 1, 2, 3, 4, 5, 6, and 7. Going down, negative 1, negative 2, negative 3, negative 4, negative 5, -6, and -7. Not that I really need those, but I'll put them in there anyway. Okay, now we're doing the sine function. Okay, so we start the sine at the phase shift, -π4 right here. And sine usually starts at 0, so that's where we'll be starting this one right there. There's your 0 for sine. Okay, now in one interval, which is π12, these are π4ths, you're going up to your amplitude, so that's going to be right here at 2. Okay, and then at another interval, which is here, we go back down to 0. Another interval, we go down to -2, the amplitude, back here to 0, and back here to +2 again, and then get out of there. Okay, all right, there. Going on the other side, we'll go one interval over, which is 2 spaces here. That will be your minimum, your 0, your maximum, and then another 0. Okay, so here is, you don't really have to draw it, but we will. Here is the sine function. Let's just talk about what it's experienced here. Okay, keeps on going. All right, there's a sine function, a vertical stretch, that's what the amplitude is, the +2 here, and a phase shift to the left 1/4 pi, but with an interval of 1/2 pi, so 2/4 pi's. So there we have our sine function sort of drawn. To do the cosecant function, once you get the sine function done, that's the work. The cosecant function is this. Okay, find your intercepts and make those vertical asymptotes. Every intercept becomes a vertical asymptote because you can't divide by 0. And I'm glad I'm in red now. Whoops, I don't know what that did. Okay, there's a vertical asymptote there, and there, and there, and there, and there. Sound like Bob Ross, don't I? Okay, and there. Okay, you got your vertical asymptotes. Cosecants, find your max and min, but go in the opposite direction. Let's see if we can choose a different color here, just so you can see where is my, there we go. Let's see if we can find another color. Let's go to black, okay, since this is in black here. This one was in red, so your cosecant is going to kiss at the max and min and then go toward the vertical asymptotes in both directions. Okay, the min here kisses here and goes in the opposite direction. This one right here and goes toward the vertical asymptotes. This one here touches there and goes toward the vertical asymptotes. This one touches here and goes toward the vertical asymptote and keeps on going that way. Okay, somewhere down here you had one picking up there. There's your cosecant function right there. You don't have to do any amplitude. That doesn't make any sense here. You don't have to worry about phase shift. You don't have to worry about period. Your sine took care of all that for you. All you have to do once you get the sine drawn and the phase shift and everything else, then everywhere you see a 0 for sine, vertical asymptote for cosecant. And everywhere you see a max or a min for a sine, that's a min or a max for the cosecant. And you just draw them in. Hand draw is fine. There's nothing you have to connect any other points. That's what you need. Pretty straightforward, huh? Let's see how they did it. Okay, I'm going to erase mine because it's sort of messing up the screen here. Begin by sketching the graph of exactly the same thing except you put sine in instead of cosecant. So let's graph that first. And for that function, the amplitude is 2. The period is, the b is 1, so the period is 2 pi, and the phase shift is minus pi fourths. That's what you have to, well, they do this by the equations, and you can do it that way if you want to. It's perfectly fine. That gives you at minus pi fourths and 7/4 pi. I sort of wish I still had mine up there. I'd show you that's how we did without having to solve the equation at all and mess around with subtracting 1/4 pi from 2 pi and getting 2 pi into 8/4 pi, and then subtract that and give you 7/4 pi. It's just a little extra work. This is pretty straightforward, okay? And you get them all. You don't have to worry about any of them, okay? If you do it the way we did, just go on and graph the sine function, okay? So the graph of the sine function is represented by the gray here, okay? We had it in red, and everywhere you saw an intercept, vertical asymptote, that is in red. Here, 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 all those vertical asymptotes, and then your maxes and mins. Oh, here comes Damien. Let's get Damien in here. There we go. Damien's here. Okay, we should be up to, that's 4, 8, 9, 10, 11, 12, 13. Should have 13 students. Let's see if we do. Yep, and nobody in the waiting room. Good deal. All right. Do you see how to do that? The work is done in doing the sine, and it's easy. We've done it before, okay? Once you get the sine done, use the put vertical asymptotes everywhere the sine crosses the x-axis. In other words, everywhere where sine is 0, and then the maxes and mins will be just interchange each other, and they go in opposite directions. That's it. Any questions? All right, that was example 4. And I can't get this slide to advance. All right, because the sine function is 0 at the midpoint and endpoints of this interval, the corresponding cosecant function, their interval they were talking about here, from minus pi fourths to 7 and 7/4 pi. Okay, we didn't worry about that. We just drew the sine. We knew it started at 0 there at minus pi fourths, and then I did tick marks every 1/4 pi, so we wanted the interval of half pi's. There you have it. That's the max. There's the 0. There's the min. Once you get it done, it's done, and you don't have to worry about midpoints and other things. It's all done for you if you do it sort of the way I did. Okay, so but if you like this way, go for it. Okay, and then what you do now is just, instead of cosecant, you put 1 over cosine. 1 over sine. Vertical asymptotes everywhere you had a 0 before. They list them out here. All I did was take them off the graph, and show where those are. And then they connect and touch. The graph of the cosecant function is represented by the black curve on the previous slide, I think that says. All right, we've done it. Now, that was example 4. They're skipping 5 before they get to the damped. Be sure you put the p in there, trigonometric functions. Okay, so let's back up 1. Okay, I went too far. I hit the wrong key. Okay, that's where I meant to be. Let's go to the whiteboard to do example 5. Any questions so far before we leave that? All right, now I've got to do some maneuvering around here, so hang tight for a moment. I'm going to move this taskbar that you can't see out of my way, and I'll move the whiteboard that you probably can't tell its limits here, but it does have them. I'll move it as far as I can, both to the left and up, so I get maximum white space to write on. Okay, and here's example 5. Sketch the graph of y is equal to secant of 2x. How would you approach this one? I'll just give you a hint. I'm going to approach it by choosing a color, or I'll let you choose a color. We've got lavender, bright red, pink, a rusty red, yellow, orange, and brown, sage green, a bright green, and a dark green, a light blue, a medium blue, and a dark blue. Pick a color, any color. Anybody? Give me a color. Have I put you to sleep already? Give me a color.
You say you had a blue?
A blue. I have a light blue, a middle blue, and a dark blue.
Dark blue.
Dark blue, okay. I've just lost my thing here. There we go. Dark blue, got it. Okay, so what would you suggest I graph before I try to tackle a secant function? What's the reciprocal of secant?
Cosecant?
No, cosine. Cosine 2x. That's what we're going to graph. So we start with our alphabet. A here, if I could get the stinking pen to write, A here is equal to 1. So the amplitude is 1. Okay. B here is equal to 2. What does that relate to? B relates to the period. And the period is what? Normally for cosine it's 2 pi, but because you got a b of 1 divide by, a b of 2 divide by 2. So that makes the period pi. Now I choose my interval. If I could get this thing to write. The interval would then be a quarter of your period. Your period is pi, so the interval now is pi fourths. Okay, your C here is 0, so there's no phase shift, and the D is also 0, so there's no vertical shift. Thank goodness. They get messy when you start dealing with the inverse function, so we usually won't do that, reciprocal functions. So let's draw my graph here. It's supposed to be a vertical axis. This is supposed to be somewhat of a horizontal axis, so it should be a straight line too. Let's pick some points here. Tick, 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 tick. Whoops. Tick, 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 tick. And to the left, negative, tick, 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 tick. I don't space them too well, do I? Okay. And we'll go up here. Okay. Now our interval, we don't have a phase shift, so the interval is just going to be pi quarters. 2 of those would make a pi halves. So 4 of those would make a pi. 4 more of those, 1, 2, 3, 4, would make a 2 pi. And then we run out of room. Back here, a minus pi quarters. Minus pi halves. And minus pi 1, 2, 3, 4 minus 2 pi. Okay. Now, Oh, Kelly must be getting bumped in and out a lot, so let me put her back in. Okay. Now, question? Okay. Since we're doing cosine, cosine usually starts at the max, right? Oh, I didn't mark my scale here. I'll just for funsies. Where in the world is my pen? There it is. Okay. Because they're so close, I'm just going to put this as a 1, a 2, and a 3. And a minus 1, minus 2, and minus 3. Okay. All right. So cosine usually starts at the max. We have no phase shift, so we'll be starting at a plus 1 there since the amplitude is 1. It goes down at one interval, 1/4 of a period. It goes down to 0, then down to minus 1, up to 0, up to plus 1, down to 0, down to minus 1, up to 0, up to plus 1, down to 0, down to minus 1, and up to 0. Obviously I didn't get my things going in the opposite direction. Down to 0 here, down to minus 1 here, up to 0 here, up to plus 1 here, 0, minus 1, 0, plus 1, 0, minus 1, somewhere down here. So this is, oh, get back there. Okay. Got too close to the, get out of there. Oh man, what is this doing? These are very sensitive screens, and I'm not a very sensitive person, obviously. Okay, so I can't find my cursor here. There it is. There we go. Still can't see it. There it is. Let's go back to our whiteboard. There we go. Okay, I'm going to try again to pick up at this point here and go up to here. This is our cosine curve here. I didn't quite make it to that max, did I? Down here, up there, down here, 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 here. Sound like I'm comforting a crying child. Here now. Okay. Whoops. Y'all aren't crying, are you? Not yet. Okay, something like that. There's the cosine function. Okay, now I'm going to choose my bright red here to be my vertical asymptotes because I don't want the secant function even coming close to those. So where in the world is my pen now? There it is. So we got a vertical asymptote here. They can get close, but they can't touch. A vertical asymptote here. Vertical asymptote here. Vertical asymptote here. Why did I draw them so tight together? I've got to draw all these vertical asymptotes. Okay. Vertical asymptote here. Everywhere it crosses the cosine function, crosses the x-axis, that gives you a vertical asymptote for secant. And I only got a few dozen left to go. I hope this is my last one. Okay. Now let's go back to black to draw in my secant function. They start at 0 at the max here. Now it goes up. This one would be going down. This one going down. Not crossing the vertical asymptotes. Getting closer and closer to them, but never touching them. That's all you do, is from the peaks or the valley, go in the opposite direction, approaching the vertical asymptotes either way you go. Make sure you make these rounded, not pointed, because all the trig functions are smooth. They're not got angles in them. They're made up of angles, but not that kind of angle. Okay, and somewhere here, that one, and that one, and this one, and this one's heading off that way. There's the secant 2x. What has happened here? 2x is a horizontal shrink. Horizontal shrink. Remember, whatever you're doing with x is in the opposite direction. Multiply by a big number, you make it tighter, a horizontal shrink. And that's why what would have been a 2 pi now is a pi for one period. Okay. Any questions on that? So that is our example 5. Oh, and by the way, every example is followed by a checkpoint. Please do the checkpoints as soon as you can after class is over with, so you can refresh what we've just went over and make it yours. All right. If there are no questions, we'll go back to the PowerPoint, which is 4.6, right? Yeah. Okay. And why in the world it does this? Let me try this and see if that works. Okay. So we did that. Now let's get to damped with a P trigonometric graphs. Okay. You can graph the product of two functions using properties of the individual functions. So let's consider this. F of x is now x times the sine of x. Okay. Now, that's the product of two functions, x, y is equal to x, and y is equal to sine x. Okay. Now, using properties of the absolute value and the fact that the absolute value of sine x is always less than or equal to 1. Sine x never exceeds plus 1 or minus 1. It's always in between plus or minus 1. So the absolute value of sine x is always less than or equal to 1. So you can write this inequality here that 0, is less than. You're basically just expanding this. They've done a couple of steps here at once. Everything's absolute value, so you know 0 has to be the minimum of that because you can't be negative. So 0 is less than or equal to this. Whoa, here comes Kelly back again. She must either be getting kicked out or she's having to leave and coming back. So basically what we're going to do is multiply, well, they did this first. 0 is less than sine x is less than 1. Okay? Then multiply every one of those, all three sides of that inequality, by absolute value x. So absolute value x times 0 is less than absolute value of x times sine x, which is less than or equal to absolute value of x. Okay. Now, this is our function here. Close. It's the absolute value of that function. Okay. So, what that says, you can take the minus x and put it on the other side of the absolute value bar, absolute value thing, and do minus x is less than, let's just see what they do. Okay. Well, they don't do anything. They won't advance. Okay, here we go. Yeah. So minus absolute value x is less than or equal to sine x. See, now or x sine x. Now you've lost the absolute value bars here, and that's less than or equal to absolute value of x. You just took the absolute value, put it over here. Now sine x is free to be anywhere between that and that, even equal to that. which means that the graph of f of x equal x sine x lies between the lines y is equal to minus x and y is equal to positive x. Okay? Now, that may not be intuitively obvious to you that's the case, but it is. That is indeed true. Furthermore, because your f of x is this, and it's equal to plus or minus x when sine is plus or minus 1, that's going to be at your half pi's. That's where sine is at the maximum or minimum. And the half pi's plus n pi. Okay? I'm trying to think if I know why they did. Oh yeah, okay. Because it's at the max at 1/2 pi and at the min at 3/2 pi. So that's why it's only pi in between, because you're not doing a full period, you're just doing max to min, min to max, max to min, which is half a period, which is plus n pi. Okay? Now, f of x is also 0, certainly when x is 0, but it's also every time that sine is a multiple of pi, n pi, okay? Which would be at 0 also. So n is an integer, and the graph of n touches the line at y equal minus x at the minimum, y is equal to x at the maximum. Those are going to be at your half pi's plus n pi. Now, I can't read this because this stupid box is in the way. It has, I think this is intercepts is what it's saying. X-intercepts at your, where it's equal to 0, okay, at n pi. So, what that means is draw your lines in there. Your y is equal to x, that's the identity function, and the opposite of that, negative x there. Those become what I consider your envelopes, and your sine function stays in between that. Now, one thing to notice here about the sine function, because over here x is negative, but then the sine x starts off being negative, negative times negative puts that up to plus. Here x is positive, sine is positive, so you start here going up this way, and then you follow a normal sine route. Here you start and go up rather than down. So basically your envelope, this is where sine reaches its maximum, minimum, maximum, and those are at your half pi, 3/2 pi, 5/2 pi, 7/2 pi, negative half pi, negative 3/2 pi, negative 5/2 pi. So everything you did before where you reached plus or minus 1 is now doing to your plus or minus x. So the factor x is called the damping factor. Now, it's damping when you're getting close to 0 this way or that way, but it's exploding in the other direction. So I don't really consider that damping going in the other direction, but that's still what they call it. Now, so the one thing to note is when you have both the x and the sine x being 0, and that would be just to the left of 0, then negative times negative is positive. So now rather than going down here, it's going up here. So that's the one little thing to watch for. Now that's how the book describes it, and it's a perfectly good description. I threw in the term of envelope because I remember that back when I was in school. But here's the other way I look at it. Think of this as a variable amplitude. So this becomes your amplitude function. Y is equal to x, and then because it goes up and down, y is equal to minus x. So that's your variable amplitude. That's where it reaches. Here comes Courtney. Good deal. I think Courtney said he had to work, and that's why he comes in at a little bit later. Okay, but Courtney's here. So Courtney, if you're here, and others who may have come in a little later, we're on in chapter 4, trigonometry, we're in 4.6, graphs of other trigonometric functions. We're now looking at damped with a P trigonometric graphs, and we're setting up top half of page 313, just about through with it. So what I was saying, I think of this as a variable amplitude. So draw those in there, and then what the sine function did to amplitude, that's where it touches up here, touches down here, touches here, touches there. It's a variable amplitude. Now, to me, that makes a lot of sense. If you don't think that makes sense, just do it the way they're doing it, and it's fine. It's the same thing. Okay. And now can't get it to advance. Well, nope. Guess I have to click on it again. All right, we're ready for example 6. Okay. Sketch the graph of f of x is equal to e to the minus x times the sine of 3x. Okay, we got a lot of stuff to do here. Okay. Now, I'm not going to carry it through gory detail as they do, but here's what I'm going to do. Let's just draw our axis here. That's supposed to be a vertical axis, and that's supposed to be somewhat of a horizontal axis. Okay. Now, what does e to the minus x do? Well, when x is equal to 0, y, or e to the 0 is 1. So it's right there. So there's 1, 2, 3, 4, 5, 6, 7. Okay. And negative 1, 2, 3, 4, 5, 6, 7 down there somewhere. Now remember, we're going to have to do the same thing down here, so I'm going to put another one here too for the other side of the envelope. Okay, and when x is equal to 1, that is 1 over e, which is something about 1/3. Oh, let me tick off my points here. Now here's where we run into some problems, people. And that's because usually your horizontal axis we put in terms of your pi's, in terms of your x's. So I guess I need to go back and get that right, and then we'll figure out where x equal 1 is. Okay. So let's go on and do that. This is your variable amplitude, so that's why I started to draw those in, but we won't draw them yet. Let's do this one next. Okay. Your A is variable amplitude, your B is 3, which means your period is 2 pi over 3. Divide that by 4 and you get the interval is, if you divide this by 4, 2 will go into 4 twice, and 2 times 3, so this will be pi 6. Okay, your phase shift is 0, and I'll certainly thank you that the d is 0 too. Okay, okay, so this is going to be pi 6, pi thirds, pi, well, let's just do that. This will be 2/3 pi, and this will be pi. So it's going to be 6 of those. 1, 2, 3, 4, 5. Okay, we're going to run out soon. So this will be minus pi 6, minus pi thirds, minus 2/3 pi, and minus pi, and then 1, 2, 3, 4. Yeah, we run out pretty soon. Okay. Now, I put those scales in there so we'll know. Here's what I go by. Pi thirds is very close to 1. If you think about pi is 3.14 divided by 3, that's going to be just a little bit more than 1. Okay, so that's why I said when x is equal to 1, and this, remember, is your x-axis here, and this is your f of x or y here. Okay, and when x is equal to 1, which is over here near here, this is about 1/3. Okay, now that's really approximate. Well, down here it would be negative 1/3. Okay, So let's do another one when x is equal to 2 here. This will be close to 1/9. Okay, so that'd be 2/3. 1/9 is going to be pretty close down here. Okay, and negative 1/9 would be pretty close down there too. And they get even closer. Let's go in the other way. When x is equal to -1, minus a -1 is 1. E to the 1 is about 2.7. So there's 2.7 will be here, but -1 would be there. So we'll just say something about right there. Okay, and then this will be 2.7 down here as well. So negative 2.7. You got to draw the envelope on both sides. Okay, and then when x is equal to -2, this will be e to the -2, minus a -2, so that would be e squared, and 2.7 squared is something less than 9. So there's 1, 2, 3, 4, 5, 6, 7, let's just go on up here, 8 and 9. Okay, I'll be able to draw it somewhere up here. So this is supposed to be 2/3 pi, not 2/2 pi. Okay, so this is going up here to something a little bit less than 9. So we'll just put it right here. And this one's going down here, and that's really off scale. So what do we have? Our envelope function, our damping function, and this truly is a damping function, is going incredibly large to the left, but getting incredibly small to the right, and getting closer and closer and closer and closer and closer to 0, but never getting there. Same thing here, coming from way down here, somewhere up here, and whoops, I went too high there. Here, somewhere I had a point there, I thought, and then it gets closer and closer and closer and closer and closer. Okay, now let's go back. Sine at 0 is 0. Sine at your excuse me. Didn't have time to get the microphone out of the way. I blew y'all out, right? Okay. At your first interval, it goes to a max. The next interval goes back to 0. Then it goes to a min. Then it goes back to 0. Back to 0. Get out of there. Okay. 0. 0. Max. And after here, it's just such little variation you can't tell at all. You know, it's just going back and forth. On this side, however, it goes from here, 0, down to a minimum. Now this time, this is always positive. So whatever the sign of sine is, that's the sign you keep. Okay, so that goes negative, then up to 0, and then up here to a max, and down here to 0 again, and then down here you're off scale. So here's what's happening here. Goes up to here. Nice smooth curves now. Don't forget to make them smooth. Don't make them pointed. And from this point on, it gets just so it goes back and forth here, getting closer and closer to 0. So you see, this is indeed a damping function in this direction. So that's how we sketch the graph. Somewhere up here, you are back to a 0 again here, and a 0 again here, and a 0 again here. This one's going almost vertical here, somewhere way down there. This one's going almost vertical here, going somewhere way up there. This one's going almost vertical here, going starting from down there. But should be a lot more vertical than I'm drawing. But they go way off scale, and they don't come that close together. So I shouldn't have even done that. So that's what we've got. Blowing up to the left, damping big time to the right. Okay. Let's see how they drew them. I think I'll erase this because it's so ugly. I Okay, we'll erase that ink. And here they consider the product of two functions, and they go through all this mess. Basically, all you have to do is graph y is equal to e to the minus x, draw y is equal to minus e to the minus x. Okay, and then use your sine function to get your zeros and your max and your min, and just connect the dots. That's what you do. They go through all this stuff, and it's fine. Ooh, I hit the wrong key here. Sorry about that. They go through all this rigmarole, and it's right. This is where you get the bottom function, minus e to the minus x gives you, get out of there, the top function, e to the minus x. So you basically plot those, and these are going to stay in between them. Okay? And who cares about this, that your functions are going to be your max and your min at your first interval and every odd interval of pi 6. After that, you don't need to do all this. All you have to do is use your graph and let it go. Okay? And then you're going to have your zeros then midway in between those. Okay? Yeah, they've said it right. It's 0 plus n pi over 3. Okay. So that is a lot of work. If you just did the e to the minus x, or yeah, like we did here, minus e to the minus x like we did there, put your zeros at your every other interval. Okay, so that would be at 0, pi thirds, 2/3 pi, pi, and going backwards, minus pi thirds, minus 2/3 pi, minus pi over here. And then your max is halfway in between there, min is halfway in between there, max halfway there, min halfway there, and then it gets so close it's hard to tell. That's what we got. And that looks a lot like ours too. Almost vertical, not quite here, almost vertical, but coming up, touching there at whatever 6 of a pi that is, and then coming down here at pi thirds of 0, at pi 6, minus pi 6 is 0, minus pi thirds of min, 0, and then go. Just use your damping function e to the minus x and e to the minus x as your variable amplitude. That's where they touch when you would have maxes and mins, and relative max and mins, that's where what they are, and the zeros stay zeros. So they're really not that bad to graph. Any questions? Okay. So now we're on sort of the summary. That was example 6. We got it done. Now we're sort of doing a summary. Below is a summary of the characteristics of the 6 basic trig functions. Okay? The sine function starts at 0, goes up from there. Remember, everything's positive in the first quadrant. So it goes up from there and reaches a max at a quarter of its period, reaches another 0 half a period, another one at 3/4, another min at 3/4 period, another 0 at the next period. So domain, all real numbers. Range, it always stays between plus or minus 1, unless you have a amplitude in there. Okay, the period is 2 pi, unless you have a b in here. Okay, cosine, only difference is it starts at 1 and goes down. Remember, everything's positive in the first quadrant, so it's starting at 1, it has to go down. A 0 at your half pi's, min at your pi, 0 at the next half pi, maximum at the next pi, and on and on. Opposite direction. Looks just like the sine, it's just a phase shift off. Domain all real numbers, range -1 to 1, period 2 pi. Okay. Tangent function, everywhere that cosine had a 0, which was the half pi's, tangent has a vertical asymptote at every half pi. Draw them in there to begin with, you got them done. Okay. They have a zeros exactly in between those half pi's. So those are the full pi's, minus pi, 0, plus pi, 2 pi, 3 pi, 4 pi, the 0 every one, and then it's going from there. Remember, everything in the first quadrant is positive, so tangent is increasing here, so it had to be increasing here too. Always increasing. Domain all real numbers except your half pi's, because that's where cosine is 0. Range negative infinity to positive infinity. It has no limit on the range. Period is pi. Tangent and cotangent are the only two with periods of pi. Now, cotangent has, because it's cosine over sine, anywhere where sine has a 0 is a vertical asymptote. So that would be at the whole pi's, at 0, at pi, at 2 pi, at negative pi, negative 2 pi, and so on, vertical asymptotes. Now, because everything's positive in the first quadrant, cosine has to be coming from positive infinity and going down to 0 at pi halves. So of course it's 0 halfway in between the vertical asymptotes, which are at your half pi's, and it's always decreasing. So domain all real numbers except your whole pi's. Your range is negative infinity to infinity, period is also pi. Now, your cosecant and your secant function, domain all real numbers for the cosecant except the places where sine is 0. Well, that's at the whole pi's. So vertical asymptote at 0, at minus pi, at plus pi. Same thing it was for cosine, okay? It is for cotangent and cosecant. They have the same vertical asymptotes. Now, if you imagine having the sine curve in there, that's where your vertical asymptotes are where the sine crosses the x-axis, and your min and the max. Say again? Did you have a question? Okay, Courtney, I think your microphone flipped on there for a moment. Okay, no problem. Okay, and the secant function, draw your cosine first. It starts at 1, and everywhere it crosses the x-axis, which at your half pi's you have vertical asymptotes, and at your whole pi's you have either the maxes or the min for the min or max for the secant. Okay? Really piece of cake drawing. And they didn't do the damped functions, we just did those. There is a little summary at the bottom of page 314. Let's do 4.6 vocabulary. I don't know if you have your books or not. I'll read them off. They all are fill in the blanks, so listen carefully as I read. I think I'll go back one slide. Okay. The tangent, cotangent, cosecant functions are blank. The tangent, cotangent, and cosecant functions are blank, so the graphs of these functions have symmetry with respect to the blank. Okay, they're talking about symmetry here, so the first blank is even or odd, and the second blank is what they're symmetric to. So what are tangent, cotangent, and cosecant functions? Even or odd? Odd, absolutely. And so the graphs of the functions have symmetry with respect to the origin. Perfect. Number 2, the graphs of the tangent, cotangent, secant, and cosecant functions all have blank asymptotes. Here they are. Those are your asymptotes. What do we call them? Which way are they heading? Vertical. Vertical asymptote. Very good. Number 3, to sketch the graph of a secant or cosecant function, first make a sketch of its blank function. Reciprocal function, you got it. Number 4, for the function f of x is equal to g of x times sine of x, g of x is called the blank factor. Damping, the damping factor. Okay, I don't know why I think in terms of cars here. Think of these as your shock absorbers. Okay, it's dampening the bumps in the road. Okay, now number 5, the period of y is equal to tangent x is blank. Pi, perfect. Number 6, the domain of y is equal to cotangent x is all real numbers such that x is not equal to, for cotangent, do you see my slide? N pi, perfect. The domain of, let's see, yeah, domain of x equal cotangent, y is equal cotangent x, set of all real numbers such that x is not equal to n pi. Okay. Number 7, the range of y is equal to secant x. Now I forgot to point that out to you when we were there. What is the range of secant x? And cosecant x the same. There it is coming into view now. Infinity to -1, union that with 1 to positive infinity. It's the things above plus or minus 1. Above and below plus or minus 1. Okay? The period of y is equal to cosecant x is anybody? 2 pi, perfect. Okay. Homework exercises here would include okay, what I would do, try to do all of 9 through 14. Okay, only the odds are in the book and only the odds are at calcchat.com, but you should be able to match those functions, all of them. You can check your answers on the odds, 9 through 13. Then do any of the odds, 15 to 37, they're all at CalcChat, 19's at CalcView. Any of the odds 39 to 47, they're all at CalcChat. They say you may need a graphing utility for some of those. Any of the odds 49 to 55, they're all at CalcChat. 51's at CalcView. 57 to 63, all at CalcChat. 57's at CalcView. Again, I would try to do all of 65 to 68. The answers to the odds are at the back of your book and at CalcChat. 69 or 71, both at CalcChat. 73 or 75, both at CalcChat. 77 or through 81, all at CalcChat. Then 83 through or 85, both should be at CalcChat. Okay.
What page is this?
This starts on page 315, and where I got to was over to 317. So 315 to 317. Okay. 87 is
4.6.
This is 4.6. That's correct. Okay. 87 is a true false. It should be at CalcChat. And you can think about doing 89. It should be at CalcChat. 91 should be at CalcChat. And 93 should be at CalcChat. All right. We don't have a lot of time left, about 7 minutes, but any questions on 4.6 before we leave it? Okay. And what we'll do now, if there are no questions, is move on to 4.7. Now, I think that should be this one. No, that's 4.6. I had 4.7 up here. It's disappeared. So, goodness, this drives me nuts. Let me get it back again. 4.7. Okay. Let's see if I can get it now. Okay. I think I have to get out of here. This is so awkward. Go back here. Now do a new screen share. Let's see if that works. There's 4.7. Okay. Now, we'll go from current slide. So let me just do that. Okay. Still in chapter 4, next to last section, 4.7. Here we're talking about inverse trigonometric functions. Let's do a quick review of math in general. After you learn to count and that kind of stuff, probably the first operation you learned was adding. Okay? And you learned those math tables like crazy, adding tables. You thought you had it knocked, and then they threw in subtraction, which undid addition. So you got that down and thought, okay, almost through. Nope. Then they threw in multiplication. Okay? And once you learned all those flashcards or however you learned it, then you thought you had it knocked until they said, nope, let's undo multiplication with division. Now, somewhere much later, you started raising numbers or variables to powers. How do you undo those? Roots. Okay? And then when we got into functions, and by the way, we got to functions like log functions, and the inverse of that would be you undo that with an exponential function. Exponentials are undone by logs. They just keep growing. And then we did any old function by finding its inverse. Okay? So we're going to talk about the inverse of trig functions here. How do we undo a sine, a cosine, a tangent, a cotangent? We're not going to really do secants and cosecants much, maybe not even cotangents very much. But let's see what they're talking about. We'll evaluate and graph the inverse sine function. We'll evaluate and graph the other inverse trigonometric functions, or at least some of them. And we'll evaluate the compositions of trigonometric functions. So we'll get there last. So let's start with the inverse sine function. What do we mean by this? Now, if you remember back in pre-calculus algebra when we did inverse functions, the requirement to do a function to have an inverse, it had to be monotonically increasing or monotonically decreasing. It couldn't back up on itself. Okay? Could not. It had to be 1 to 1. Okay? In other words, it had to pass a horizontal line test. Every function passed the vertical line test. A 1-to-1 function must also pass the horizontal line test. Well, if you think about how a sine function looks, it repeats itself all over the place. It backs up on itself here, 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 here. Every time it changes direction, it's changing from increasing to decreasing. So therefore, the only places that sine is 1 to 1 is where it's strictly increasing, like here, strictly decreasing here. Sharika made it in today just by the skin of her teeth, okay? Just got in on time. Well, got in today, we'll put it that way. Welcome. Sharika, we're in chapter 4, trigonometry, 4.7, inverse trigonometric functions on page 318, okay? And we don't have but 2 minutes left, okay? But glad you're here, okay? So basically, we have to identify only a portion of the sine graph which is 1 to 1. We will choose, or they have chosen for us, minus pi halves to pi halves. In that part of the domain, sine is strictly increasing, okay? It does flatten out here and here, but it doesn't back up on itself. You don't go any further than minus pi halves to pi halves. That's the only place we're going to define the inverse sine function when we get around to doing it. Okay? I have to click on the slide. Okay. However, when you restrict the domain to the interval minus pi halves to pi halves, and notice here it does include the endpoints. There's equal signs there. corresponding to the black portion of the graph, the following properties hold. On that interval, negative pi halves to pi halves, the function sine x is strictly increasing. On that interval, negative pi halves to pi halves, y is equal to sine x takes on the full range of values from -1 to +1. So you've covered all the possible values. And on the interval, minus pi halves to pi halves, y is equal to sine x is 1 to 1. Okay? So, on the restricted domain of minus pi halves to pi halves, sine y is equal to sine x does have a unique inverse function called the inverse sine function. Okay? Now, they represent it two different ways. Okay? The old way in my mind was arc sine. Okay? That's extra writing. When we did inverse functions in precalculus algebra, you just did f to the -1. So why don't we just say inverse sine, meaning sine to the -1. That doesn't mean 1 over sine, that's cosecant. That's not what we're talking about here. This is a function inverse. So this -1 does not mean reciprocal, it means inverse function. So that's the only sort of advantage of arc sine. You wouldn't get that confused. But look, you shouldn't get it confused anyway, because functions with a -1 mean inverse. The notation sine to the -1 is consistent with the inverse function notation f to the -1. And that's the only way you can say that. You don't say arc f, okay? So the arc sine notation, arc sine of x notation, read as arc sine of x, comes from the association of the central angle with its intercepted arc length on a unit circle. Oh, sure, that makes it clear, doesn't it? You know, to me that's really foggy. So arc sine of x means the angle or the arc, okay, whose sine is x. Now that's getting to the meat of it here. And we just run out of time, so we'll pick up next time with this slide right here. It starts with both notations, and let me see if I can find it in the book. Yeah, right about there. Okay, so that's where we'll begin next time. Any questions on what we did so far today? All right, we did.
Yeah, I have one question.
Sure.
You said homework. You said 9 through 14, right? Or you said 9 through something?
Okay, this is in 4.6, right? Okay, in 4.6, I say do all of 9 through 14, though only the odds are going to have the answers in the back of the book and at calcchat.com. It's just because those are matching, and you should be able to match them all. The other place was 65 through 68. Again, they're matching. Only 65 and 67 will have answers in the back of the book and at calcchat.com, but you should be able to figure out how to match those up. But don't sweat it if you can't. You can just do the odds if you want to, but it's pretty easy to do the rest of them. The rest of them are all the odds. Is that what you're asking?
Yes, sir.
Yeah.
We're in week 7.
We are in week 8. In fact, at the end of this week, that's midterm, right then, okay? So we are getting close to having our second test. I would like to have had that done by midterm, but we'll still get there, I think. Okay, not by midterm, but we'll get there. Okay, good questions. Any others? All right, we'll pick up then here next time. Any other questions before I stop sharing? I think I'll stop sharing now, unless someone has a question on this slide. And if there are no questions, further questions, I'll end the meeting for all of us. Any questions? All right, we'll have a good couple days. We'll see you on Thursday. Same time, same station. Different key code though. Okay, bye-bye.